Gnanam paramam dheyam. Knowledge is supreme.
So this is for just completeness. I thought, let me put the data for you. Why this iy and x, ix plus y, all these things comes in, minus x minus iy. So this is because if you see the spherical harmonics, y1 0 up to this normalization is cos theta. Cos theta is nothing but the z component, proportional to the z component. y1 has an e to the I phi, which you can write it as cos phi plus I sin phi, right? And there is a sin theta. If you resolve them into components, what you get here is minus of x plus iy. And if you look at y1 minus 1, it is x minus iy. Okay? Clear? You remember these things. So this is why this is for the position components. You can write for any vector components in the same way, saying that it is a rank 1. The superscript is denoting my rank 1 here. Instead of putting k comma q, I put a superscript for the rank, and subscript is for the q values. It's just a different notation. Some books follow these notation, so you should know what exactly it is. So just seeing this for the position vector, which is proportional to z, you can call this to be the z component. Similarly, you can call the magnetic quantum number, the q equal to plus 1 component, to be exactly similar to this, which is what we have written here. And the last one, there is some subtlety of normalization, and the convention followed in the normalization is this. Probably I had it in that slide, but when I wrote it on this, I didn't write it. Is that right? I had it on the, yeah, there is a square root 2 here, which should also be incorporated. Is this clear? At least the rank 0 tensor is a scalar, should be clear to you. Rank 1 tensor is a vector, and the vector, keeping your knowledge on spherical harmonics, which is applicable for position operator, you can try and write any vector operator in that notation. Instead of writing x component, y component, z component, you will like to write it as k comma q as 1 comma 0, 1 comma 1 and 1 comma minus 1, or you can put a superscript and a subscript, where superscript corresponds to k and subscript corresponds to q. Is that clear? So this is for a tensor of rank 1. So this I have already said. There is a lot of resemblance between spherical harmonics and the k comma q, and similarly formally for any other vectors other than position vectors, you can have a similar behavior of how kq behaves under rotation. That's the same way the operators will behave in the similarity transformation. So then we have to look at, you did the CG coefficients by taking 2 spin half particles or 2 particles with angular momentum J1 and J2. Why can't I compose 2 tensors and see what happens? Right? This is what you will ask. Suppose I have a tensor, I take another tensor. If I combine these 2 tensors, that is like an uncoupled state, which is what we call it as a reducible tensor. Why reducible? It is a raw thing where I will reduce it and make it like a trace, antisymmetric. This is what we did and made it into irreducible tensors. Okay. So I am bringing in the concept of reducible and irreducible, just like uncoupled states. Right? Uncoupled states are the ones which you have just taken a tensor product and written. But then you also said the coupled state has some properties, like when you took the 2 spin half particles, the spin j equal to 1, all the states there, you can go by ladder operation of j equal to 1 only, and all the states were symmetric, right? And then the spin j equal to 0 state we found by orthogonality with 1 comma 0 state, and then we found that it is antisymmetric. So there is some kind of a separation, and each of those states is what we call it as a separate module. It's a separate module. So let me try and say formally what we mean by that, and that is what we're going to do by composing tensors. So let me take few minutes and try and tell you some of the jargons. If you read books, you will get to see them. So this is what we did: J1 M1 tensor product of J2 M2, which we called it as a coupled state. Let me suppress the J1 J2. So this is uncoupled, okay. And then we had another one which was Jm, which for convenience I tried to put this bracket, which I called it as coupled. This is also 4-dimensional for J1 equal to J2 equal to half, and this one can be written as J equal to 1 M and a sum with J equal to 0 and 0, right? This is what you saw. And this one was 3-dimensional and this one was 1-dimensional. So this is like a scalar state, or a scalar, like a scalar operator, or an analogy with a scalar operator, or a singlet state, and this singlet state remains as a singlet state under rotation, okay. Because even if you do the e to the j plus operator, j minus operator, it is nothing happens. Exponential of that will be like an identity operation, right? E to the power of I j dot theta by h cross on j equal to 0, 0 will give you what? The same state. This is behaving like an identity operator. Singlet state is unaffected by rotations. This is similar to your scalar operator, which remains the same under rotations. And this one will transform under rotation, right? The j equal to the state, this will transform under rotation like a spin 1 state. And the same thing will happen for operators which are vector operators. But in the operators, you have to do a similarity transformation. State vectors transform by U operator, operators will transform by U dagger operator, U. All is the modification. So you can see that there's some kind of a ringing that it tells you that a total 4-dimensional representation in the uncoupled basis, you can resolve it having some specific properties under rotation, a state which is invariant under rotation, another state which is behaving like a vector under rotations. 3 components. So this resolution is what we did by the CG coefficients. Remember, we did the CG coefficient where we did this resolution. Now I would like to do the same thing for operators. Okay, so this is what I was indicating in the last lecture, that if you take 2 vectors, all the operators will have only integer j's. So that's why I'm calling k and q. And so if you take t of k1 q1 and take a tensor product of t of k2 q2, okay, this one is formally similar to, there is an analogy to k1 k2 q1 q2, the similarity. But you should know that these are operators, these are states, okay. That similarity tells you that this dimensionality of this will give you a tensor of what rank? So 1, k1 plus k2 formally, right, but it will be a reducible tensor. What do I mean by reducible? It's a raw tensor where you have combined them, but now I have to resolve with respect to the rotation properties. Resolve them. How will you resolve? Again using the same CG coefficients, and break it into a KQ, or correspondingly I could say it is T of KQ. So it is a linear sum going from K equal to K1 minus K2 to K1 plus K2. It's a linear sum. So by this linear sum I mean T of mod of K1 minus K2, the corresponding Q, take a sum of T of mod K1 minus K2 plus 1 comma Q dot dot dot. Finally the last one will be plus K2 comma Q. This sum which I am writing is what we call it as some kind of a direct sum. Like this is a direct product. This is what we call it as a direct sum. Each of these are irreducible tensors. Okay, all of them separately. Okay. So this piece, when I just take a product like an uncoupled state, it's considered to be a reducible tensor. This is exactly what we did. We took an AI and a BJ. This was rank 1, a vector AI and a vector BJ, the components. And then I wrote formally this as some tensor of rank 2. This is a reducible tensor. This is vector of rank 1. You understand what I am saying? This is also a vector of rank 1. You had two vectors of rank 1. You took a tensor product of two vectors and you got a raw tensor of rank 2. That's called reducible tensor. Okay? And that reducible tensor, you can write it as a components or resolve it into irreducible tensors, and each of those components will have a specific behavior under rotation. This raw one will not have any specific behavior. You can break it into subcomponents so that a trace of that matrix is nothing but A dot B, that is invariant under rotation. One which is invariant under rotation is like a singlet state which did not change under rotation operator. So that scalar is an irreducible tensor pulled out of the tensor product of two vectors. Okay. And how will you pull it out? You can use the CG coefficient, same methodology, and pull out the irreducible tensors from the reducible tensor which you have just got by raw multiplying the two separate tensors. When we did two vectors, you take vector A and a vector B. When you just compose them, you are not doing dot product or cross product. You are just formally taking AI with BJ, where I could be anything, one of the 1, 2, 3 or J could be 1, 2, 3. How many components are there? 9 are. 3 cross 3, which is 9. Right? So the 9 can be written as a 3 by 3 matrix. I can call it as a rank 2 tensor, or I can formally write it as TIJ. But this rank 2 tensor is a reducible tensor. I want to resolve it and write it as components which has specific behavior under rotations. Okay. To do that, what I will do is, I will try to resolve it this way. If I do it this way, this is resolution. You remember that when you did this uncoupled state to go to the coupled state, this resolution gave you the CG coefficient. The same CG coefficient will help me to do this. Is not uncoupled state, this is called reducible tensor. I can break it into irreducible components. Is the spirit clear? You should go back and look up Schiff now. Okay. It's very well said. In symmetries of quantum mechanics, there is a section where the tensors are very well written. Now, if you go and read it, you will understand. Okay. You can also do mix and match. You can have a tensor operator and the state also. Nobody tells you that you should only look at, because now you can go back and forth. You don't need to only work with tensor operators multiplied with another tensor operator. You can also have a tensor operator operating on a angular momentum state. So those composition also can be done. Okay. So please go back and read Schiff, and then you will try to appreciate what I am trying to say. Okay. But at least you should be clear that this is a reducible tensor, and you will use the CG coefficient just like we use the CG coefficient to break this into mod k1 minus k2 in steps of 1 to k1 plus k2. The same thing you have to do it for the tensors also. So TKQ is an irreducible tensor where Q takes values. This is just again I am trying to repeat. Similar to a state vector k comma q. Just like we take tensor products of two vectors, you could take tensor product of the two tensors which we take are trivially, this TKQ is a irreducible tensors. So product of two irreducible tensor will give you a reducible tensor, okay, in general. So whenever we take tensor product of two TKQs, each one is an irreducible tensor, but when we take a product, we will get a new tensor with the rank looking like k1 plus k2, but that is not a irreducible tensor. So this we did elaborately last time. I am again repeating it here. We can take tensor product of two vectors and we can write Iij. This is in our notation now, it is a reducible tensor. Correct? Ai was an irreducible tensor of rank 1. Another, if you take the same vector Ri and Rj, each one is an irreducible tensor of rank 1, but the product which gives you a moment of inertia tensor is a reducible tensor. And you can break that reducible tensor into pieces. This is what I was saying, but I didn't do the CG coefficients here, but you can do this also. Okay. So if you do the CG coefficients, it will give you pieces. One is A dot B, which is like a trace. Another one is A cross B, which is like an antisymmetric piece of this Iij tensor. The last one is the remaining. Out of the 9, you already have one component here. A vector has 3. 3 plus 1 is 4. How many are left? 5. A symmetric traceless tensor will have 5 independent components. With trace it will be 6, but without trace, if you want to reduce the trace to be 0, then one more component is constrained, right? So it is 5 components. So once I get 5 components, you can see a resemblance when I took a tensor product of two spin 1 states, which was 9-dimensional. The allowed J values are J1 plus J2 to J1 minus J2. So it is 0, 1 and 2. So this is what you would have written for the states. This is exactly what I have tried to resolve here and rewrite your states, rewrite your operators, tensor product of two operators as a resolved irreducible components. Okay. So let me just put it for you in more complete thing. So I am going to take Ai Bj. Let me call this as this T, if you are getting confused, let me put it as Cij. Okay. This Cij, I can write Cii plus Cij minus Cji by 2 Is this correct? I have not done anything. I have written the Cij in a little easy looking fashion. Nothing more I did. This I can write it as 1 by 3 trace of C times delta Ij. This I will write it as Aij. Okay, this bracket. This I will write it as Sij. Can someone check trace of Sij is 0 or not? Can you check? So what did I do? I just rewrote the same element which was on the left hand side is a reducible element. I resolved the same element into 3 pieces, delta Ij, yeah, I put it as trace C times delta Ij so that the Ij elements are ticked. So I have just written any component as formally as adding pieces. As he is pointing it out, I can write this explicitly as this way so that the indices are all visible. Yeah. So you can use CLL and then put a delta Ij. Is that what you are saying? So CLL means it's summed up. Okay, so I've just tried to rewrite it in a fashion where can an antisymmetric tensor under rotation become a symmetric tensor? That such kind of chaos happens, then you will have, two del R's when you have it is symmetric, and if you have an epsilon ijk, you put it to be 0 because the product are all in two different spaces. I'm sure you would have played around with Levis-Vita symbols. Suppose I give you an epsilon ijk and I give you a pj pk. What is this? This is symmetric. This is antisymmetric. It's always 0. So the symmetric product and antisymmetric products, antisymmetric tensors and symmetric tensors are in two different spaces always. Okay. So only thing is that the trace term is invariant under rotation, or it's behaving like a singlet, and then you have an antisymmetric tensor which is actually an axial vector kind, but it behaves like a vector under rotations. And then you have the remaining, which can be written as a symmetric traceless tensors. This has 5 independent components and this has 3 independent components. Agreed? And this is just 1. So this, which has 9 components, and the 9 has come out of 3 into 3. One vector has 3 components, another vector has 3 components, and this 9 components can be resolved. It's exactly the way we do the CG coefficients. You can resolve it and write it out, and you will find that the rank 0 plus rank 1 plus rank 2. So what have I tried to show now is that, at least with the vectors I have tried to show this, given you an indication. So what I am trying to say is, if you take K1 Q1, take K2 Q2, you can write it as in terms of the CG coefficients, with the K going from mod K1 minus K2 to K1 plus K2 CG coefficient. I can write that also explicitly, but you understand what I mean. Okay, and this Q is restricted. Q has to be for a specific element. So whenever we take 1 comma Q and 1 comma Q1 and Q2, you will get this as some linear combination of K going from 0 to 2 CG coefficient of this is what I am saying. Okay. We did this elaborately for spin half. For spin 1 also you can do this elaborately, and this is exactly the way this will also happen. And we can verify, and I will give you an example. I will show this example clearly. This I have not done it now, but we will see it now. Okay. But is the spirit clear how things are going? So this is the way I resolve, seeing how the rotation properties are, and each one is an irreducible tensor, and you can see that there is a lot of resemblance by taking tensor product of states, which will give you an uncoupled state which is 9-dimensional, and you can resolve it in the coupled basis which will allow 1-dimensional, 3-dimensional and 5-dimensional. 2j plus 1 is the dimension of j. Clear?